Welcome everyone to the second day of the workshop. And the first speaker today is Boaz Barak, who's going to tell us about pseudo-distributions, optimization, and the quantities for it itself.
Thank you. And yes, I'll talk about I'll talk about commutative optimization, and it's the sum squares hierarchy. But as we see, it can be applicable, like Aram said, to non-commutative probability problems and quantum information. So in particular, I'll actually talk about exactly one of the problems that Aram mentioned yesterday, quantum separability, one of its variants, and actually one of the examples where the sum of squares hierarchy right now gives something that we don't know how to get by these net kind of algorithms. And more generally, I want to show a different way to think about designing algorithms based on this optimization, which I find it useful, and while it's mathematically equivalent, I find it a useful way to look at these kind of problems, and this can apply more broadly, and if we get time, I'll also show how it applies to the problem of robust statistics. Okay, so some of you are computer scientists, some of you are not, but probably you've seen some kind of, maybe, or you've known there are these, if you teach a basic algorithms class to students, then the way you teach them algorithms typically works like that. You explain to them that the way it works is that someone defines some computational problem. This is the input, this is the output. Then you stare at the ceiling, get a bright idea, find an algorithm, and then you analyze the algorithm and prove that it actually succeeds in solving the problem that was stated. And probably I could say the same thing about solving a mathematical problem, right? You're given a problem, you think hard, you come up with a solution. And of course, the thing that bothers me is the hard thing about it, which is this part. So I would like to try to see if we can remove this thinking from algorithm design. So this talk will explain a different approach to algorithm design where we can remove the creativity. And the idea is that we really in some sense start with the analysis, but we start with analysis existential that, for example, shows that there is a solution and translate it into a computational analysis. So for example, in applications in statistics or machine learning, you can think of, you start with a proof that your observation determine the unseen variables, and you automatically translate this proof into an algorithm that from your observations recovers the parameters. And we'll see two corollaries of this approach. One is this better than brute force algorithm for the best separable state problem, and the other, we'll see, I hope, robust mean estimation. The other is not by me, and this is the other is an area where there's lots of deep work going now on the robust estimations of parameters. And in some sense I'm cheating. You see there is still some creativity in the analysis, but the algorithm is chosen for us. Okay, so if you know of optimization-based algorithms for combinatorial optimization of relaxation, so the typical view is the following. We want to find some x in some set. So I'm talking about the feasibility problem, but you could also talk about the optimization problem, some x in the set that satisfies some certain objective value. And this is what we want to do, but maybe this set S is a set we cannot optimize over. Maybe it's some integer set that we cannot optimize directly over. So we encompass it with a bigger set, S tilde. So here, for example, maybe we want to optimize over the integer points, but we encompass it over a bigger set, and then we find an element in this bigger set, in this relaxed set. So, for example, maybe we we have this integer set of integer points, and we find the point in the polytope that encompasses them. And then we want to find a rounding algorithm that takes this point from the larger set and maps it into the point from the original set that we wanted. And this talk I'll talk about a different way to view optimization, and the idea is the following. We want to find x in S, we want to do the same thing, and what we do is we are going to assume that we can find simple statistics, which would be basically low-degree moments of some distribution d tilde, which is not an actual distribution, but a so-called fake distribution. I'll explain a little bit more what it means later. And the idea would be that we would want to come the algorithm to sample from S. This should be S, using these simple statistics with simple analysis. And this at the moment maybe doesn't exactly make sense. I hope it will make sense more. And you can even think, what does it mean, this fake distribution? And the way I prefer to think about it is, this is the computational posterior. This is not a distribution, it really captures your knowledge. So, for example, you could think of, suppose you have, you have this equation, fx equals y, and it's an equation that maybe has a unique solution x. So you're given, this is what you know, and this is what you don't know. So perhaps this equation has a unique solution. So the distribution over the solutions is just a singleton, it's just a distribution, there is only a solution. But because you're computationally bounded, from your perspective, you might think there is actually entropy here. Maybe you would say, okay, maybe if x is a vector, you would say, I have some biases, I have some, looking at this f, it tells me that the first coordinate of x is likely to be small, and the second coordinate is likely to be large, and there is some correlation between the third and the fourth and the fifth, but I don't know more than that. So in some sense, this distribution is really a way to capture the uncertainty we have as computationally bounded. But maybe this will make more sense. So what do you mean by this kind of pseudo-distribution? So the idea in designing algorithm based on this paradigm is, I think it starts with the observation that, it's better to be rich and healthy than poor and sick. And Marx and Engels, I think, were one of the first people to make this observation. And what does it mean? What does it mean in the context of algorithms? It means if someone gives you extra power, it's easier to solve problems. So the way we are going to do these design algorithms is we want to solve a problem. We'll use an unreasonable algorithm that gets extra power to solve it. And we want to then solve it with an algorithm which we can actually run, which is the sum of squares optimization. And the idea is that if we prove that this unreasonable algorithm solves a problem, and we do so with a simple analysis, then this simple analysis will translate over and will show that even a weaker algorithm can still do the job. And yeah, this is kind of the general philosophy. Now, don't worry, this philosophy will end in one slide, and we'll talk about an actual computational problem and an actual result. So we'll take this hypothetical algorithm, and maybe it's an algorithm that runs in exponential time, or it's an algorithm that you give it kind of hints about the solution, which is again kind of unreasonable. And we're going to lift the proof of correctness of this hypothetical algorithm to show that actual algorithm succeeds. Okay, and I think the degree L sum of squares proof. So I'll think of sum of squares as a proof system, which is just a dual view to the algorithm. So you can think of the way you can think of the sum of squares algorithm. You can think of it in two ways. You can think, as an algorithm, you can think you have a polynomial constraints on x1 and xd, and what it outputs is a moment matrix, which is like fake moments. It's not an actual distribution, but it pretends to be a distribution that satisfies this constraint. This is the point of view that Aram was mentioning yesterday. And another way is to think of it as a proof system, where your basic axiom is really that a square cannot be negative, but only a square up to a certain degree. And the positive Stennelsat says that if you allowed all degrees, then you could prove any true statements about any true inequalities or of polynomials you could prove using the system. But if you have bounded degree, then this is the bounded degree. It's still surprisingly powerful. And one way to think about these fake moments is that, yes, they are fake, but you cannot prove using this limited proof system that they are fake. So any argument you make about these moments where you pretend they are real, if you restrict yourself to using this proof system, then this argument will carry through even when they are fake. And now I'm going to talk about quantum optimization. One kind of way to try to see how it relates is, Bell's inequality, and maybe just as a warm-up because it's still early. So Bell's inequality in quantum information theory, it's just the following purely classical statement. It says the following: if you have a game where Alice gets Alice gets a bit A, Bob gets a bit B, and Alice outputs XA and Bob outputs YB, then if we play this game where Alice and Bob give us $1, get $1 if the outputs agree, unless but the output needs to disagree if both inputs were 1. Right. So this is this game where basically you say you have A and B, and Alice and Bob should agree here and disagree here. So they can win this game with probability at most 3/4, and that's what's written here. So it's if you say if they win $1, so R divided by 4 would be their profit, and their profit would be half on average, because they'll pay $1 in one case and win in the other cases, and this is Bell's inequality. The way you prove it is one way to prove it is the following: you write this quantity, you express it as express it as squares. You do Cauchy-Schwarz, and you say this R value is at most square root 8, which is 2.823. And then what you so far you've just used Cauchy-Schwarz, and then what you say, okay, this is these are just adding or subtracting integers. So R has to be an integer, so it has to be at most 2. Right? It cannot be 2.8. And that's the proof of Bell's inequality. And why did I? And the surprising thing is that in quantum experiments, if Alice and Bob have shared quantum entanglement, they can do better. How much better they can do? They can do exactly the square root 8. So one way to think about it is that yes, quantum nature might not follow Einstein, and nature has quantum, but it does respect Cauchy-Schwarz. So the sum of squares proof actually gives us the right. So Cauchy-Schwarz is the sum of squares argument, and the sum of squares bound actually gives us the bound on the quantum value. This rounding steps is outside the sum of squares framework, and that somehow exactly is the difference between the classical and the quantum value. Okay. So now I'm going to talk about a concrete problem, this separable state problem. So basically this is somewhat of a repetition of what said, but helpfully I'm using a different notation, so to keep you on the toes. Okay, so you think you have a system on Q, you have a system of two qubits. Or you can think of it of two systems, each of which can be in one of these states. So the set of all mixed states in the system is the set of all density matrices, is all matrices that are d squared by d squared, or, with trace 1 and positive semi-definite. And the set of all separable states is some subset of it, is the subset that I talked about, is the set of all matrices that is complex combination, you can think of it as complex combination of these vectors like U, V, V, U, or another way to think about it is, it's a convex combination of A tensor A, where A is a rank 1 matrix of the form, UV transpose or UV star. But in this talk, whether we work on C or R doesn't really matter, so you can just pick your own favorite fit. So this is the set. So the set of all separable states is a subset of the set of all states, and one, if you want, various entanglement set has no entanglement if it's in step, and the various entanglement measures are how far is it from the set. And what we're going to talk about is the following problem. We want to okay. Maybe I'm going to talk about what I'm going to focus about is the best separable state problem, which is this H set problem that I talked about, which is the following: you're given a measurement, and you want to compute what is the separable state that maximizes this measurement. Right. So if you wanted to ask what is the general quantum state that maximizes this measurement, it would simply be the top eigenvalue of n. This would, but we want to know what is the separable state, so that would maximize the probability that this measurement accepts this state, which is captured by just the trace of M1. And we are actually going to focus on a special case where we want to distinguish between two cases. One case is that this measurement, there is a separable state that passes this measurement with probability 1. And the second case is that every separable state passes this measurement with probability at most 1 minus epsilon. Okay, so this is the problem, and the result I'm going to talk about is a better than brute force algorithm for this, something that runs in 2 to the times square root d as opposed to 2 to the d. So one way, by the way, to think about this thing is to say that in the second case, if every separable state passes this measurement with probability at bounded away from 1, then this measurement is an entanglement witness. If you pass this measurement with probability 1, then that certifies that you have entanglement. And the entanglement witnesses are often useful if you have a system and you want to certify that it has entanglement. What you want to do is to give some measurement that has this property. And now if you don't know quantum or don't like quantum, here is another way to just think about it, which completely is classical. What you're given is, forget about this M, you just think of the top eigenspace of M. So think of it's some linear subspace, so you're given some linear subspace W over the space D squared. And you have the manifold of all rank 1 matrices. And your question is to separate between two cases. Case 1, this subspace W contains a rank 1 matrix. And case 2 is every rank 1 matrix has at least epsilon distance from every rank 1 matrix has at least epsilon distance from this subspace. Okay, and the problem, of course, is that it's a non-convex set, so that's why it becomes like a. Okay, so yes, so this is basically this problem, and the brute force algorithm runs in 2 to the d. Like Aram said yesterday, if you want really, really small epsilon, then this is NP hard. And if you want constant epsilon, then Aram and Ashley Montanaro showed that it requires at least d to the log d. And if the measurement has this special form, then exactly like was discussed yesterday, then you can do it in this time. but we didn't know something better than 2 to the d for general measurements, and this is what we do here. And we basically, we're not, like I said, like I promised, we are creativity free, so we outsource the creativity in creating the algorithm to Pablo. What we do is just analyze the sum of squares algorithm and show that it does 2 to the square of the, that it runs in time 2 to the square. Okay, and what is this approach? The approach is very, reasonable, like, as you would think, as you would design an algorithm. So what do? You dream that you have access to moments of a distribution over solutions. Then you use these moments that you dreamt about to obtain the answer, and then you wake up and you hope that you still are holding in your hand, the actual solution. So this is very reasonable thing to do, right? You suppose you need a lot of money, then it seems like a reasonable thing to do. You would, when you're sleeping, you dream you have a lot of money, you grab onto it really, really tight and wake up and you hope you're still holding it in your hands. So, so this is basically going to be our approach for solving this. So what does it mean? So first of all, I'll move to the reals because I don't know how to work with complex numbers, and I'll move to symmetric matrices, but it's the same. So the idea is the following. We are going to assume, we're going to dream that someone gave us degree L moments of a distribution over the solutions we are looking for. So we are looking for a matrix, a rank 1 matrix in this subspace. We are going to imagine that someone gave us a distribution over exactly the object we are looking for, rank 1 matrices in this subspace. And let's see if, this is basically just allow us to compute the expectation of P of U, where, U is this P. So it allows us to compute the expectation of P of U for every polynomial U of degree at most L. And now let's try to solve the problem using this thing. So suppose someone already gave us a distribution over the solutions, but that someone didn't give us a way to sample from this distribution, but just the moments. Can we find an object? Can we find a matrix that is at least close to W? Okay. So maybe before I do the first attempt, let's just make sure that this is now a mathematically a precise problem, even though if it seems a little bit convoluted. Then right. So the input is some subspace W of R squared. There is a distribution D over U transpose in W, which we get, expectation of P of U or U from D for every polynomial of our choice as long as the degree is too small. And our goal is to find a small W such that W transpose is close to W. And what does it mean close to W? You can think of in Frobenius norm, say epsilon in Frobenius norm, where this is unit vector. Okay, so this is a well-defined problem. And how do we do it? So the first thing we could try to do is we could, we're trying to find a matrix. We have distribution of matrices. Why don't we just take the average? We can definitely compute the average. So we could compute the expectation of Ui, Uj for every I and j. So we can just compute the average of this distribution and find this matrix. Now, will A bar be in this subspace W? Yes, right? It's, a distribution over matrices in W, and it's a linear subspace, so it will be in W, so that's a good thing. Our question is, will it be rank 1? No, right? Generally, if you take an average of 2 rank 1 matrices, it's not rank 1. That's almost guaranteed not to be rank 1 matrices, unless you took the same one. So it might not be, might is even an understatement, it will not be rank 1. That's the worst way you could take, you could try to think of a way to get rank 1 matrices by taking average of rank 1 matrices. Because the problem is really that this set of rank 1 matrices is not convex. So that's so the average doesn't work. And what we want to do, unless we had a very special distribution, which was basically maybe just a singleton. And what we want to do is show we can actually convexify this distribution. What does it mean, convexify the distribution? We show that for every distribution, and this is really the technical heart of this paper, we show that for every distribution over rank-1 matrices, we can find a degree square root D polynomial, such that if you reweigh the distribution based on P will also be positive, by the way. It's not super important, but convenient. So if you reweigh the distribution based on P of A, so you give every matrix a weight P of A, then now the average is almost rank 1, in the sense that there is a rank 1 matrix which is of epsilon close to it. Or another way to think about it is that the top eigenvalue of this matrix will be the top eigenvalue of this matrix squared will be larger. The sum of all other eigenvalues squared will be at most epsilon times the top eigenvalue squared. Okay, so in general what we do is we take this very non-convex distribution and somehow find a way to convexify it by only reweighing it with some polynomial of degree at most square root D. And since we are allowed to compute moments up to square root D, we can do that. Okay? Yes?
I'm a little bit lost. So, using the sum of squares, you get a pseudo-distribution.
Yes.
But this is about distribution.
Yeah, this is where the part where this is the part where I use my inception paradigm. So, so I'm going to do the entire analysis over distributions, and then hope it still works with pseudo-distributions.
Got it.
And that part is actually like the part that where what you will do is basically after you do your entire analysis, then you go back and look at what you've used in your analysis. And as long as you only use tools that involve low degree SOS, so then everything you have said about distributions actually works for pseudo distributions. So that's why the technical heart of this theorem is this statement, which is about an actual distribution. That's the hard thing actually to prove, or maybe not that hard, but that's the thing you need to prove. But at least is the theorem clear? So maybe I'll before. So is the statement just clear, right? So I want to say yes.
How does, I don't know if you talk about this, but how does P depend on the distribution?
So we'll see. That depends a little bit, not a lot, but we'll see how to construct P.
So is there like an easy version of the theorem for degree D? Like if I just take the polynomial to be like a to the D or something?
Yeah. So basically, if you had degree D, that's a great question. So if you had degree D, you can essentially make the distribution a singleton or something.
Like do the characteristic polynomial? Is that what you do? Or?
Yeah, I mean, even if you just took a random direction B and you just look at the polynomial P of say U is VU to the 100D or something like that, then in that direction, in that random direction, there would be one way to think about it is that if you took a random direction, then there would be distribution D over rank, this is distribution D over essentially vectors.
So when you say P of, so to relate that to P of A, you'd say P of A is like bra V A ket V?
Yeah, something like that, yes. So, I mean, because it's very easy to get from A to U, vice versa, sometimes I say P of U instead of P of A. A is like U transpose. And generally, you can discretize, so you can think of D as supported over at most. So D is a distribution of a matrix of the form U transpose. And after discretizing, there is at most 2 to the n of them, right?
Yeah.
So there are 2 to the d of them. So there's at most 2 to the d of them. Now, if you say hit this with a random vector, you're basically getting normal variables. And now, if you, one of them will be the maximum. It will be the maximum by a very small gap. By, you know, it will be multiplicatively, it will be probably only something like, you know, 1 plus 2 to the minus d bigger than the next one over. But if you raise this to the power 2 to the d, then so if you raise this to the power d, that turns out to be enough to somehow basically isolate it. So everything, what will happen is that everything that has dot products, say, you know, 1%, dot product less than 99% with the top one, is likely to get very small weight. So essentially, you're making this distribution into a singleton. Yeah.
What's the dependence on the degree on epsilon?
What?
What's the dependence of the...
It will be polynomial in epsilon or something.
Polynomial.
Yes.
So,
Yes.
just one more
Yes.
question. So, like, if I had a distribution over rank 1 matrices,
Yes.
and my goal ultimately was to compute the expected value of some cost function, and then establish that there is a rank 1 matrix that achieves at least the
Yes.
value, then that would be straightforward without this, right? So,
Right. So, but in some sense, if you were, yes, but here it's kind of important that you're looking at the search problem. So you somehow want to show that if you had an algorithm that just given the moments produces an actual solution.
oh, you actually want to find the rank 1 matrix? Is that the point?
Yes.
Yeah. Okay.
So we have an algorithm that gets the moments and finds the rank 1 matrix, and then we show, because this analysis of this algorithm only uses sum of squares, then therefore, and actually this is maybe even cleaner in the robust statistics, which I might not get to, but if I do get to, you'll see it. If not, yeah. Okay, so the inspiration for that is this Lovec's growth rank theorem in communication complexity, but let me kind of skip that discussion. And the idea is the following. So here is something that's the basic component. This is not good enough, but this gives us the basic component. The idea is, say I pick L to be something like, you know, 1,000,000 times square root d or log d times square root d, and I pick a random unit vector u0, and I reweight the distribution by p of u, which is u dot u0 to the power 2L. So let's try to kind of heuristically see what it will do. So what will be lambda 1 squared? So lambda 1 squared will be roughly the best vector to hit. So the distribution, this is a right-only board. So roughly speaking, you know, if you look at expectation of U transpose, and you hit it with U0. Yes.
Free upgrade.
So this is at least, let's say, since U0 is a unit vector, this is at least lambda 1 is at least this, right? U0 can be a test vector. It's at least, so lambda 1 will be at least lambda 1 will be at least this thing, right? This is the distribution, or in general, now we rewrite with P of U, so this will be, lambda 1 will be at least P of U, P of U, this, so this is lambda 1, this should be an inequality. Lambda 1 will be at least this. And now we compare what's the Frobenius norm of the remaining part, the part that's orthogonal to U0. And which you know, we can write in this way, because you know, we look at the orthogonal part will be, we look at the P of U transpose U P of V transpose. That's the Frobenius norm, right, of this matrix. I just write it as the dot product with itself. and combine its, its expectation of P of U, P of V, U V squared. So here, but here we just project to the part orthogonal to the U0. And heuristically, what does it look like? The dot product of this U0 behaves like a normal. And these are unit vectors, so it behaves like a normal with over d-dimensional space. It behaves kind of like a normal with standard deviation 1 over square root d. And here what we are doing is basically u0 to the power 2l plus 2. So it's like so we are looking here at normal to the power 2l plus 2 squared. And here what we basically have is something independent. So we're looking to the n to the power 2l squared, and n to the power 2, that should also be squared. So this is really just the difference between these two quantities. And generally, what will happen is that we compute what is the moment of a normal. This is like 2l plus 2, this double factorial, just taking the products of the even things, and so this is really what you're comparing, and what you get is basically the difference. Sorry, I think there is there wasn't this way. So the difference here is basically because of this plus 2. We get an additional benefit here of L squared, and we get here we pay this sigma squared. And here this is just going to be just the O of 1. Okay, so basically the calculation, which you have to review, but basically the calculation is that if because sigma squared is at least 1 over d, if L squared is larger than, so basically the point would be the following: if L squared is going to be larger than, if L squared is going to be larger than d, much larger than d, which then it's likely that this term, lambda 1 squared, is going to dominate the sum of everything L squared. So that's basically the calculation. And now the idea is that, okay, and then maybe let me do it kind of, the idea is you do some kind of iterative construction. So you take your distribution, you hit it with this random vector, and then one of two things happens. Either the top eigenvalue now dominates everything else, and then we are happy and we're done, or when you created this large lambda 1 value, you also lifted some other eigenvalues, and now the Frobenius norm grew. But then this cannot happen too often, because every time you do it, you say you double the Frobenius norm, and the Frobenius norm cannot double, more than logarithmic number of times. Log d should be there. So this was a little bit rushed but the point is that there is an analysis of showing, and the analysis is not very complicated, and that's at the end of the day, this analysis kind of uses various things like Cauchy-Schwarz and Helder and these kind of things. And then basically this allows us to do what David asked about. So we pretend we get these moments, but then we show that because this proof is in the SOS framework, therefore, even without getting these moments, we could basically design, fake moments using the sum of squares algorithm and run this algorithm. Okay, so and that's the proof. And I want to show you, and this is basically the bottom line. But I want to show you the reason I was a little bit rushing through this is because I also want to talk about these other examples which might more neatly kind of demonstrate this. So let me skip. Let me talk about this other example, which is learning with outliers. So okay, so suppose. Let me talk about this example. Okay, so here is another if you lost me before, here is a completely different question, but very, very natural one. What's the most basic problem in statistics? You're given m samples from a distribution, and you want to compute the mean. You want to compute the population mean. You want to compute what is the average value in this distribution. But you're given the empirical distribution. You want to empirical samples, and you want to do the mean. And that's very, that's the obvious thing. What do? You output the empirical mean. But what if only 99% of the samples came from the actual distribution and 1% are complete outliers? So even you can even think of the more extreme case, but we'll not think about it here. That what if 1% came from the distribution and 99% are outliers, and you can still do something meaningful. But even if 99%, this is the empirical mean can be something very bad to do because we are in high dimensions. So think about the following case. Suppose your empirical mean is 0. Right, so you have all these points, high-dimensional points, with average 0. You can add very few outliers, but put them all in the same direction, and that will push the empirical mean. It will push it in that direction. So with 1% outliers, you can make the mean bad in a dimension-dependent way. This is this kind of calculation. Basically, if you're in n dimensions, with 1% outliers, you can push the mean out with square root n square root n badly. And it turns out that this is not inherent. You can actually estimate the mean within constant accuracy in this kind of setting. You can actually estimate the mean with up to constant error when you have 1% errors. You just don't take the empirical mean. That's just not the right thing to do. Okay, and the first person to notice this was Tukey in 1960s. That you can do robust mean estimation. But he gave an exponential algorithm, which basically said something like you take your samples, you enumerate over all subsets of say 90% of the samples, and you calculate the means, and somehow from them you can see that one of those is not like the other. And the results, which is not mine, but some different groups of researchers have shown it, is that you can reprove Tukey's algorithm with this exponential thing, but show that this has a constant degree sum of squares proofs. And once you do that, then automatically you get a polynomial time algorithm. So you take this kind of exponential algorithm that enumerates over all sets, and you prove that it will work with a low degree sum of squares proof. And automatically, this means that you can make this exponential time algorithm a polynomial time algorithm. And this really extends a lot. This is an area where there are like, lots of things happening. And actually, if you're interested in that, I'm sorry, I'm going to have to, after my talk, rush over to teach my 190 undergrads waiting for me. But Prayag is my grad student. Prayag over there in the back is one of the people that are very knowledgeable about all of this literature. So let me kind of show you a little bit how it works. So the idea is the following: how do you take a sample of? How do you take a set and see if it's bad or good? And one way to do it is the following: you look at You look at the empirical covariance matrix, and you look at its empirical covariance matrix, and you look at its spectral norm. And if the spectral norm is large, you say, okay, something is fishy about this set. And the idea is the following: you can show that if you have a set S that doesn't contain outliers, then the spectral norm of the covariance matrix will be bounded by some constant. And the other thing is that if the set is large and the spectral norm is bounded by a constant, then the empirical mean from this set is an accurate empirical mean. Okay, so here is an exponential time algorithm. Enumerate over all subsets, all say subsets of 90% of your samples. Compute for each one of them the empirical covariance matrix. And if you will find one of them that has bounded spectral norm, and that one, if you output the empirical mean for that one, that will be a good estimate of the population mean. Yes.
I just wanted to have maybe 5 minutes.
Okay, 5 minutes. Yes, very good. Yes. So this is a theory, a proof, I haven't shown you the proof, but this is basically. So this is the idea. Now the other idea is that if I show you that this proof if I can prove to you this proof using the sum of squares algorithm, then I basically get an algorithm out of it. And the idea is that yes, we can certify this by constant degree sum of squares, and that will give us an efficient algorithm. So okay, so let me show you the proof for this. So if it was okay, so this is let's say let me ignore the first part. This is some concentration bound, and this is basically some concentration of matrices. Okay, so this is the heart of the matter. I want to prove this thing that if say the spectral norm is at most 2, then my population mean and the empirical mean is correct. And I want to prove this. So let me start just by proving it, and I'll prove it only in one dimension because I just want to give you the flavor of the proof. So okay, so I want to say the following thing. So I have 2 random variables, x and y, so this is at least 1 minus epsilon m. So the difference between x and the probability that they differ is at most epsilon, and the variances is at most 2. So now I want to look at how far can the means be. And you just do kind of calculations. You do Cauchy-Schwarz and AMGM, and you get to the conclusion that you can bound how far they can be by their variances, and it is most 10 epsilon. And the thing that the actual steps are not very important. You could you could do it yourself. But what is important is what we use here. We use Cauchy-Schwarz, we use AMGM. On those are both sum of squares arguments. So the main thing is basically whatever argument you use to prove this, it's a sum of squares argument, and therefore we can get an efficient algorithm. And I think so maybe I just leave the slide of like other approaches where people have used. This is a list that keeps going, but other problems where people have used the same type of approach. And that's it. Thank you.
Questions?
Yes.
So how much creativity do you think there is in rounding?
So yes, I hope that eventually we will have like a canonical rounding algorithm. I don't see a reason why we shouldn't have. So I hope we can push all creativity to the analysis.
Yeah.
We haven't done it yet, but I hope that we can show that there is an optimal rounding algorithm that is always the best thing to do, and therefore all you really get. And maybe the optimal thing is indeed you get your moments. You have to hit them with some polynomial, and then just take its its average.
Yeah.
or sample from, there's another thing you can do is sample from a distribution matching the first two moments. That's something, sample from a Gaussian that has the same two moments as you.
The questions?
Well, if not, then let's think once again. Then we'll take a 7-minute break.